Electromagnetic theory often feels like an exercise in managing abstract symbols. You open the textbook to Maxwell's equations and find a notation that can easily hide the physical behavior it is meant to describe. Vector calculus provides the geometry for these equations. These formulas map out how fields move, curve, and flow through a coordinate system. To use these tools effectively, we need to examine the physical intuition behind the gradient, divergence, and curl operations. Building this spatial framework is the most reliable way to systematically set up and solve complex vector integrals. Measuring a field requires setting microscopic rulers. Here, differential length, dl, is a vector along the edges, and area ds points normal to the surface. These are distinct from the differential volume, dv, a scalar representing the internal 3D space, regardless of direction. With these defined, we apply the del operator. Think of del as a mathematical machine designed to measure physical change in a field. The first operation is the gradient. If you are on a mountain slope, the gradient is the single steepest vector pointing straight up the incline. It takes a scalar field, like altitude, and returns a vector. Next is divergence. Imagine a water sprinkler. Divergence measures the volume of water radiating away from that central point. This operation evaluates a vector field and returns a scalar value representing the source density. Then we have the curl. If you place a paddle wheel in a river current, the curl measures the rate of spin. It returns a rotational vector pointing along the axis of rotation. Translating the abstract del operator into these specific motions, ascending, radiating, and spinning, prevents fundamental errors when setting up electromagnetics problems. To evaluate a field's total effect along a continuous path in space, we use a line integral. This is represented by the closed-loop path L and the differential dl vector shown here. We can see this in practice using the wedge path from example 3.9. The loop is defined by 4 distinct corners, A, B, C, and D. The total field accumulation is calculated using the closed line integral of A.dl. Rather than calculating the entire loop at once, we decompose the path into 4 distinct segments, AB, BC, CD, and DA. Breaking the path down into these segments simplifies the math, turning one spatial problem into 4 single-variable calculus steps. Moving along the first segment from A to B follows a curve, changing the angle phi from 30 to 60 degrees. With the radius locked at 2, the angle is the only changing variable, yielding a differential length vector of r d phi a phi. When we take the dot product with the field, we integrate purely with respect to the changing angle. For the second segment, we move in a straight outward line from point B to point C. Here, the angle is locked at 30 degrees, and only the radius is changing. This results in a new differential length vector, dr, in the AR direction. The dot product now isolates the radial components, leaving us with a simple integral with respect to the radius. Successful integration depends entirely on matching the differential dl vector to the physical direction of each specific segment. A technical distinction in these operations is often overlooked, leading to errors in field derivation. Divergence is a scalar operation, and curl is a vector operation. Interchanging their results destroys physical meaning. This is central to Helmholtz's theorem. A vector field is defined by its divergence and curl. Zero divergence is solenoidal. Zero curl is irrotational. To summarize, lengths and areas are vectors, while volume is a scalar. Divergence measures scalar source density, and curl measures vector circulation density. If this visual approach clarifies the core concepts in your textbook, please subscribe for more engineering and physics video guides.